Students typically just totally ignore the camera stuff after a little while, and it becomes just as if it's not even there. Okay? So what we're going to do is we're going to start today with the introduction to dynamics, and I'll spend a few minutes discussing what the course is about, and then we'll move into actually working some problems in an area called rectilinear motion. We'll try to be done by 5:20, 5:30 at the latest, because I think there's another class scheduled in here after that. All right? So dynamics as a field of study really didn't come into fruition until 100 years ago or so, maybe 120 years ago. And a lot of the mathematics and a lot of the development of it actually happened probably back in the 1800s. And some of the laws that you've been exposed to in physics courses and some of the concepts and names of formulas and so forth that you'll see in this course are in honor of people that did that development back then. That development started as a result of learning or developing the concepts of calculus. Newton and Leibniz did that initial work. And it appears that Archimedes actually had understood a fair amount of that, but those documents were lost from back around 300 or 400 AD, I believe. With the early days of the Industrial Revolution, what engineers would do back then is they would come up with an idea, they would build something, and then they were using steam power oftentimes, or water power, or wind power in ships and so forth, to actually get things to move after they built it. Once they say, imagine this, imagine that they cast a nice big old flywheel that they then hooked up to some steam power where they could get that thing to, say, start spinning. They just built it. They would build it, they would fire it up, get it moving, and then oftentimes those things would fail, oftentimes catastrophically. And they're scratching their head going, why did it fail? So then what would they do? They'd go and build another one that they thought was tougher. Fire it up, and maybe it worked just fine. And oftentimes a lot of engineering has been done that way. You just build it. If it doesn't work right, or if it fails, you just rebuild it, change the design a little bit, see if it works. Well, they started wondering, well, why are these things failing when we start to put them into motion? And so that's when they started using mathematics to go through some calculations to sort of discover why these things would fail. When you put mass into motion, what you've learned in physics is that there are forces created. There are dynamic forces created. And that's what causes, oftentimes, the response, which sometimes is unusual and strange, and other times it corresponds or works very well with your analytical calculations. For instance, throwing a ball through the air, you can model that as you've done in pre-calculus and first-year calculus courses. You can model that projectile motion. And you've seen it in physics as well. And we'll actually go through those kind of calculations again here. And pretty darn accurately, the equations that you write, neglecting air resistance, pretty closely will track the kind of response that you'd see by throwing that ball or shooting that arrow or firing that gun. Neglecting air resistance. Sometimes, though, things aren't as apparent. We would not be able to put satellites up into orbit. We would not have radio and television or anything if it wasn't for our analytical abilities to be able to actually do the mathematics to make the predictions, and then based on those mathematics and those designs that we come up with mathematically to then build something that actually will work. So I worked in the space and missile systems field a little bit while I was in upper division in graduate school at Aerospace Corporation down in Los Angeles. One of the problems at the time was a lot of the military and Air Force satellites, or rockets that they were trying to put satellites up into orbit, they started pogoing, and then they would self-destruct from the kind of pogoing forces that were created, because those structures, those cylindrical structures, were not designed to be accelerated or jiggled vertically up and down. And so they would go up and they'd self-destruct. Well, they had to go back and redo calculations and figure out what was causing that. It turned out there was some pulsing going on in the engines and the thrust created by the rocket engines. And that's what's creating these instabilities in the structures. That's one simple example. They were then able to do the analysis and figure out what was going wrong and correct that when in the rocket engine design. So that's just one simple example. What we're going to do in this course then is to help you develop your ability to do this analysis line by line to be able to actually solve real-world problems. And the book that we use and the kind of problems you'll see in here are really very practical. They oftentimes call this program at the freshman, sophomore year at universities or here at the community colleges, they call it a pre-engineering program. And I've been contending for many years there's nothing pre about this program. This is engineering. The strength of material stuff some of you studied last term, the statics you did last fall, the course here in dynamics, this is the stuff that they oftentimes are using on the job in engineering. So in this class, what we're going to do is we're going to take a particle. In other words, we're going to treat an object that has mass as if it is a point mass. It could be treating an entire airplane or a rocket as a single point mass. Okay, that's called a particle. We're going to do two things in studying particles. We're going to study the area called kinematics. And what kinematics is the geometry of the motion. The geometry of the motion. We're not concerned with the forces that are on it. We're just concerned with the geometry of the motion. We might know how the path followed by a particle. We might know its path. From that knowledge of that path, we can find its first derivative, which as you know is its what? Velocity. Okay, we can find its first derivative, which is then going to be its velocity. And then, once we understand its velocity profile, we can take its derivative and figure out its accelerations. Okay? So, sometimes you don't know the displacement field. You may start with the acceleration field. Then, to figure out what the motion is, you have to do what to the accelerations? You integrate that over time to get you back to the velocities. And once you understand the velocities, then you can integrate again and come back to what the displacement field is. Okay? So that's the geometry of motion of particles, called the kinematics. Okay. You need to know that stuff really well, and I put a whole lot of emphasis on that area in this course, the geometry of the motion. If you know that really well, then we can go and grab Newton's second law or variations on it and start to look at what forces created that motion. Or we can take and have knowledge of the forces acting on a particle and figure out the geometry then. Okay? So if you know the kinematics, you will be really well set to then learn the kinetics of the particle, which is then when you start looking at the forces or the impulses or the work that's done. So that's the distinction between kinematics and kinetics. Kinetics is where you start looking at the forces. It could be the momentum. It could be the work, energy type of trade-off. So we'll spend quite a bit of time in this area for this course. Most of the course is in this area. Near the tail end of the course, we'll start studying rigid bodies, which you had some introduction to in your physics sequence. And we'll be looking at some different ways of studying how a rigid body behaves. So any questions so far with just a general overview? Okay. So we're going to start out with some really basic but important concepts in an area called rectilinear motion. And so we'll go ahead and get going on that. And actually, I think I better do one more thing. You all know what G is little g? Yeah, acceleration due to gravity. Okay. So I want to start actually there, since a whole lot of engineering occurs here near the Earth's surface, and a lot of it has to do with the weight of an object, and then you put that object into motion, and in addition to its weight, then you get dynamic forces created. So we need to understand a little bit about that item G that you've used in physics. Okay. Newton came up with Newton's law of attraction between masses. So if we have a mass, let's call it M, and some other mass, why don't I call it ME, then there is a force of attraction, an actual force of attraction that exists between those masses. Mass M is attracted towards mass ME with some force, we'll call it capital F, and likewise ME is attracted towards this other mass. That law has a gravitational constant we call capital G, which is the universal gravitational constant. You can look it up in the book. It's a pretty strange looking value. But what Newton figured out is that the force of attraction is directly proportional to the product of the masses and you remember the rest of this relationship from physics?
To the square of the radius between them?
Inversely proportional to the square of the distance separating the mass centers. Okay? The gravitational constant is necessary to establish a proportionality equation or formula here. Okay. Now, Newton also figured out that the acceleration a particle might carry times its mass is equal to a force. So let's take and do this. Let's imagine we have an object near the Earth's surface. It could be your dynamics book. It could be you as a person. And you carry so much mass. Under the acceleration of your attraction towards the Earth, and that's got to be equal to this attractive force. So if we set these equal to each other, assuming this is the mass of the object of interest, times the acceleration, it's going to be equal to this thing. And we'll assume that R happens to be us near the Earth's surface, or the object that we're of interest to us near the Earth's surface, and the R is the radius to the mass center from here we are at the Earth's surface to the center of the Earth. That's about 3,960 miles, or you can look it up in the index of the book, or the tables in the back of the book, if you want to see it in meters or kilometers. So notice then that the mass of the object of interest disappears, and we have this now in terms of the mass of the Earth and the radius of the Earth. This we call the acceleration, the absolute value of the acceleration. And it's going to be g me over r squared. This turns out to be roughly 9 1/4. I'm sorry. No, that's not right. 9.825 or so, I believe. $9.825. And this is going to be in units of meters per second squared. Does that feel okay to people? Okay. This does not account for the fact that we live and our entire Earth's surface is on a rotating sphere. Okay? It's not a perfectly shaped sphere. It's a little wider in the middle through the equator. So this is for the Earth, the non-rotating kind of an Earth. Now, what happens is we have to make an adjustment to this value to allow for a couple of things. One is the fact that the Earth is rotating. That's the primary one that's doing it. And so what we do is we make an adjustment to this to handle most engineering calculations near the Earth's surface, and we use 9.81. And you can look in a dynamics textbook and you can see that this value is going to be pretty accurate for an Earth where this is our equator. Here's our polar axis. And the fact that the Earth is in rotation like this value is going to be fairly accurate for anywhere on the Earth's surface. Now, what would you expect to happen if you were standing, say, right at the North Pole or right at the South Pole, where all you're doing in 24 hours is turning around in a circle like this? Are you going to have any dynamic effect by being there, just turning around in a circle, versus, let's say, you were sitting out here on the equator and traveling the circumference of the Earth in 24 hours, moving at over 1,000 miles an hour? Wouldn't you expect there to be a difference here than up here? Okay, absolutely. Yeah. So, and then if you are at different latitudes, and that's measured up off the equatorial plane, that's your latitude angle. Like here in Eugene, Oregon, we're around 44 degrees north latitude. When you drive up I-5 heading towards Portland near Salem, I think just north of Salem, there's a road sign there that says you're halfway to the North Pole or you're at 45 degrees north latitude.
So if G equaling 9.81 meters per second, does that assume a latitude? 45 degrees is 9.81 at the equator?
This is what we use for reasonable engineering calculations anywhere on the Earth's surface.
Except the North Pole.
No, actually anywhere, this is going to be adequate for most calculations. If you would look, let's take a look here for a second. I don't know how this will show up. Bring that back down a bit. If you look across the bottom of this graph, here we are at different latitude angles at the equator versus up at the pole, north or south pole. The 9.825 reading is be right up along here. That would be for the Earth not rotating. The variation is actually something like this relative to a rotating Earth. And so what we do as you move through the latitudes, you can see that there is actually a variation in that gravitational acceleration at the Earth's surface. And so on the equator, it's down right near 9.78 and varies as high as then up at the pole about a little over 9.834 or so. Okay? So what we do for most engineering calculations, which usually takes into account significant assumptions, is we use a 9.81 value no matter where you are on the Earth's surface. Now keep in mind, every calculation we do in engineering has assumptions made. And this is reasonable for many engineering calculations, just using a 9.81 value. All right? What happens